Hi, everyone, and welcome to Module 10, Lesson 3. This module, we're going to start our conversation on acids and bases. Now, a lot of basic information about acids and bases you should already know. You should know about pH. You should understand the different properties of acids and bases, okay? So you've seen acids and bases before in your life. So real quickly, what are some properties of acids? We know that they're sour. Let's see, do you know of any acids? Yes, I do. I know there's citrus acid, there's vinegar, there's stomach acid. So there's lots of acids that we know. And then we've seen acids in class: hydrochloric, hydrofluoric, hydrobromic, and then we got the polyatomic ion acids. And remember, when we talked about our acid nomenclature, acids are symbolized with the H plus in front, or you can see them as the H3O plus the hydronium ions, which we're going to see here coming up. Properties of bases: bases are bitter. When you touch them, they feel slippery. Some bases that we know: ammonia, baking soda. Anything hydroxide is a base, because remember when we talked about our base nomenclature, hydroxide, that's our polyatomic ion hydroxide, that makes it a base. And then there are three different definitions for acids and bases. There's Arrhenius, Bronsted-Lowry, and then Lewis. In the Arrhenius acids and bases, just say that acids will donate hydrogens and bases will donate hydroxide ions in water. Okay, great. But that isn't encompassing of things like ammonia. Ammonia we know is a base, but it's not going to break up and give off a hydroxide ion. So Arrhenius is not a very inclusive term. Bronsted-Lowry is a much more inclusive term. Bronsted-Lowry acids are substances that donate a proton, and bases accept the hydrogen pair of the proton. Okay, so we're giving off and accepting hydrogens. And that's more of an inclusive definition because it will include things like ammonia that don't follow along with the Arrhenius definition. And then the third one is a Lewis acid and base. They accept and donate an electron pair. We're not going to discuss them at all because they get a little more complicated. We're going to keep it real basic with what we're doing with this. So, strong acids. Strong acids and bases, the strength is not connected to the concentration. Super important that we understand that. I could have a strong acid with a weak concentration or a weak base with a strong concentration. Remember, concentration is molarity. The strength of an acid or a base determines how well it will dissociate or break up into its ions. Strong acids, hydrochloric, wait a second. Hydrochloric, that's chlorate. So that's chloric acid, perchloric acid, hydrobromic, hydroiodic, nitric, and sulfuric acid. Wow, I had a real big brain fart there for a second. Strong bases are group 1A and 2A hydroxide. So anything in group 1A or 2A with an hydroxide, and that will be a strong base. Now, we saw our equilibrium constant expressions, our KEQs, when we talked about equilibrium. With acids and bases, depending on which one it is, they have an acid dissociation or a base dissociation constant. So strong acids and strong bases dissociate completely. Their acid dissociation constant and base dissociation constant are 1. Boom. Ka and Kb found the same way. Concentration of products raised to their coefficients divided by concentration of reactants raised to their coefficients. So we've already seen this. Weak acids and weak bases do not dissociate completely. That's important. Examples include acetic acid and ammonia. Acetic acid is a weak acid, and it does not dissociate completely. So we would take CH3COOH, react it with water. It would become in equilibrium with the acetate ion and H3O plus. That's how I know this is an acid, because this hydrogen goes off there and gives me the H3O plus. I'll do it up here. Ammonia reacts with water in equilibrium. So the water is the acid here. So one of those hydrogens goes over there. It gives me the ammonium ion and the OH minus ion. Okay, and that's where we get that, making it basic. So conjugate acid-base pair is two substances that can be related by donating and accepting a hydrogen ion that are in equilibrium with each other. What is the conjugate acid and conjugate base from the above examples? Okay, so for acetic acid, we know is an acid, and the water acts as a base here. Okay, so the acid turns into the conjugate base. The base turns into the conjugate acid. So if it has and I'm going to write this over here, if it has a positive sign, that would be acidic because it wants to give off. If it has a negative sign, it is basic because it wants to absorb. It wants to get a hydrogen ion to make it normal. Up here, we know ammonia is a base, and that means water acts as the acid. So the base turns into the conjugate acid, and the acid turns into the conjugate base. So you can see how they are related. Okay, so being able to identify those, very important. Now, from those examples above, you saw that in one of them, water was an acid, and in the other one, water was a base. Well, water is what we call amphoteric, which means it can act as either an acid or a base. Water also does this thing where it can self-ionize, and because it could be an acid or a base, it'll actually react with each other and turn to its ions on its own. The water dissociation constant, so Kw, so Ka is the acid dissociation constant, Kb is the base dissociation constant, Kw is the water dissociation constant, tells us how well water dissociates. We can also use it to determine the Ka or Kb. So Kw is equal to the concentration of the H plus times the concentration of the OH minus, and that the Kw is 1.0 times 10 to the negative 14th. You can also use Kw to determine a Ka or Kb. If you know one, you can find the other. What was I going to say about this? It's fine. So we know our pH scale goes from 0 to 14, 7 being neutral. 0 to 7 is acidic. 7 to 14 is basic. Okay, we know that. Can the pH be below 0 and above 14? Yes, it can. This is just a scale that we use, but it doesn't mean it's like definite. And let's do some examples of calculating pH. I do realize, and I still haven't changed it, but I didn't even write what the equation for pH is. It's the negative log of the H plus concentration, or you can do the pH is the negative log of the H3O plus concentration. So we're given all hydrogen ion concentrations, we can calculate the pH. For this one and this one here, it's 1 times 10 raised to a number. When you have something that's 1 and you're trying to find the pH with an exponent, the negative exponent is the pH. So the pH for that one would be -5. The pH for this one would be 7. Don't believe me? Put it in your calculator and see if I'm right. So for these ones, you can look at the exponent and get an idea of where it should be. It should be close to -5. So let's see, pH is equal to the negative log of 3.1 times 10 to the 5th, which is -4.51. And then this one, negative log of 2.0 times 10 to the -7th, which gives me 6.70. Okay, very straightforward, very simple. The negative log of the H plus concentration. when you put it in your calculator, pay attention because you're probably going to forget to put the negative sign in front. So pay attention to that. So what's the pH of a 3.2 molar nitric acid solution? Nitric acid is a strong acid and therefore dissociates completely. So if I have 3.2 molar of this, when it breaks up into its ions, I'll have 3.2 molar of this and 3.2 molar of this. So if I'm calculating the pH, it's just the negative log of 3.2, which happens to be negative 0.51. There you go. Pretty straightforward. In case you were wondering, pH has no units. There is a way to do sig figs with pH. I'm not going to hold it to you, but I will tell you how to do it. The number of sig figs in your answer or in your concentration is how many decimal places in your pH. Okay. However many sig figs in your concentration tells you how many decimal places in your pH. Again, I'm not going to hold it to you, but if you want to do it, that's how you do it. Okay, on this one, I have them fully right there, what POH is. It's going to be the negative log of the OH minus concentration, and therefore pH plus POH gives me 14. So if I calculate, if I want to figure out like the pH of a base, I would have to find the POH and then use the pH plus POH equals 14 to determine what the pH is. So I have to, since this is a base, a strong base at that, I got to do the negative log of 0.08 molar, which equals 1.1. Now, if you got that answer and you thought that was the pH, you should think to yourself, that doesn't make any sense because that's an acidic pH and sodium hydroxide is a base. So then we do pH plus 1.1 equals 14, and therefore the pH, excuse me, 12.9. Okay, now this next one is a little bit different only because if you look at the equation, it is a strong base. I get two of these, okay? So if I have 3.8 times 10 to the negative fourth, based on my stoichiometry, this is going to be 3.8 times 10 to the negative fourth times 2. So to calculate the POH, it can be the negative log of 7.6 times 10 to the negative fourth, which gives me 3.12, and therefore the pH is 10.88. Okay, so pay attention to your balanced equations because not everything is in a 1-to-1 ratio, and therefore you're going to have to do something a little bit different. Let's do a couple more problems as examples. What is the pH of a 3.9 times 10 to the negative fourth molar sulfuric acid? This is a diprotic acid, which means it can dissociate 2 hydrogen ions. Polyprotic acids will dissociate more than 2. So H plus SO4 negative 2. So again, this is 3.9 times 10 to the negative fourth. So this is 2 times 3.9 times 10 to the negative fourth. So my pH is equal to the negative log of 7.8 times 10 to the negative fourth, which is 3.11. Okay, next question. What's the hydrogen ion concentration of a solution with a pH of 3.9? To determine your concentrations for the ion, so if I rearrange the pH is equal to the negative log of the H plus, I rearrange it to solve, and that's what I look like. If you wanted the hydroxide ion concentration, it's the negative log of the, oh, what am I doing? Nothing good. That's what I'm doing. 10 raised to the negative POH. Works the same way. So in this case, it's going to be 10 raised to the negative 3.9, which gives me 1.26 times 10 to the negative fourth. We need units. It's concentration, so molar. And this one, the H plus concentration for a pH of 13.5. So and that should make sense to you. That's an extremely high pH, very basic. Therefore, there's going to be a very small amount of the hydrogen ion in it. Okay, last two examples. So we're going to have to use rice tables for it. So this is why it's important that we did the rice tables first. It's going to make this so much easier. So if you want to calculate the pH of a weak acid or a base, you have to use a rice table. Because they do not dissociate completely and form that equilibrium, I have my double-sided arrow, and therefore I can do a rice table. So we'll start with our R, acetic acid. At equilibrium, so this was, or that my initial concentration. I'm going to draw a line for water. Since it's a pure liquid, it does not go into our equilibrium expression, and therefore I'm not even going to worry about it. I start with none of those. I lose this, I gain this, I gain this. At equilibrium, 1.5 times 10 to the negative third minus x. This would just be x, and that would be x. So we'll do our Ka, because it is an acid, which is 1.8 times 10 to the negative fifth, will be equal to x squared over 1.5 times 10 to the negative third. We're still neglecting. For those of you who are like, whoa, why'd you skip a step? Okay. It is good if you want to write out your Ka expression first. I'll write it up here for you in case you still need it. Okay, so multiply both sides by 1.5 times 10 to the negative third, and then take the square root, and it will give you x, which the only thing I care about in this, if I'm trying to solve for the pH, the concentration of the H3O plus, which will give me 1.6 times 10 to the negative fourth molar. And then, so everything that we've just done has been the same as it was for the equilibrium. I just have one extra step of now taking the negative log of your x, which gives me 3.80, which should make sense to you because it is an acid, and so I have a relatively low pH. Great. One more, and this one will be for a weak base. Done exactly the same as a weak acid, but you've got one extra step. You have to actually calculate the POH first, of course, and then the pH. So we want to calculate the pH of a 1.00 molar solution of methylamine with a Kb of 4.38 times 10 to the negative fourth. Now this R is not something that I would expect you to do because you don't know what happens with this methylamine. If you didn't know methylamine was a base, you're given the Kb. That's telling you it's a base. So what happens since it's gaining, the nitrogen actually is able to accept another hydrogen to give me that hydroxide ion, which is the thing I care about in this, so I can end up calculating the POH and then the pH. Minus x plus x plus x. Again, It's just a 1-to-1-to-1-to-1 ratio, and so I'm subtracting it and gaining it. The coefficients would go there if it was anything other than 1. Then I guess I'll write out the KB for you. Plug everything in that we know. 4.38 times 10 to the negative fourth is my KB, which is x squared over 1.00. Again, still neglecting the x. X will end up equaling the concentration of the hydroxide ion, which will give me 2.09 times 10 to the negative second molar. So POH is the negative log of this number. And then the pH is, whoops, I guess you'd probably want to know what this number is. 1.680. I'm following along with my sig figs. 3 sig figs in my concentration, therefore it will have 3 decimal places. And so my pH is 12.320. Again, this is a base. That pH should make sense to you. And that's it. That is it for these notes. Remember, pH, negative log of the H plus concentration. That's all you have to do if you have a strong acid, or base would be the pH, POH, yeah. But for weak acids and weak bases, Rice table, okay? That's going to be your big takeaway from here. Weak acids and bases require the Rice table. But if you have any questions, please make sure you ask them. Work on your homework assignment. Okay, again, these Rice tables, you just got to do them in order for you to get better at them. And then I'll see you later.